We can solve matrix equations for missing variables just as we would solve regular algebraic equations for variables. So for example, if we had the equation 5x equals 15, we would solve that by dividing both sides by 5 to get x equals 3. However, with matrix operations, there's no matrix division. Instead, we want to think about using the inverse matrix. So thinking about this algebra equation, again, 5x equals 15, another thing that we could do in order to solve this equation would be to multiply both sides by the inverse, which is 1/5. Multiplying by the inverse cancels the 5 in the same way, and we get the same answer of x equals 3. It's just thinking about the problem differently, involving inverses instead of division. So that's what we want to do with matrices. Example 1, solve the matrix equation ax equals b for x if a equals 2, 1, 4, 3 and b equals 9, 28. So in order to solve the equation ax equals b, just like with this algebra example, we want to multiply both sides by the inverse of a in order to get x by itself. Multiplying by the inverse of a makes this left part the identity, and we're just left with x equals a inverse times b. Now it is important that we multiplied by a inverse at the front, at the left side of this equation, because we had to cancel out an a that was on the left side. It also matters that it's on the left side of the b because the order of matrix multiplication matters. So now we have our solved equation, x equals a inverse times b. So we're going to multiply a inverse by b, and first we need to find a inverse. We can do that using the equation, although there are other methods, which is that a inverse equals 1 over AD minus BC multiplied by DA opposite B and opposite C along the left diagonal. For our matrix A is 2, B is 1, C is 4, and D is 3. So we first find AD minus BC using those numbers, which would be 2 times 3, which is 6, minus 4 times 1, which is 4. So AD minus BC is 2. And we get that A inverse is 1 over 2 multiplied by, in order to get the inverse matrix, we switch the original along the right diagonal. So instead of 2, 3, we have 3, 2 along the right diagonal. And then we change signs along the left diagonal, but keep the numbers in the same place. So 1 turns into -1, 4 turns into -4. Then we can multiply this out, multiply everything by 1/2 in order to get our inverse matrix. So A inverse equals 1/2 of 3, which is 3/2. 1/2 of -4 is -2. 1/2 of -1 is -1/2. And 1/2 of 2 is 1. So that is our inverse matrix A, A inverse. So now we can plug that into this formula that we solved for x. So x is going to be equal to A inverse multiplied by B. Okay, and now we do matrix multiplication. So we multiply first row by the column. We can do this matrix multiplication because this is a 2 by 2 and a 2 by 1. So those middle numbers match, and our answer is going to be a 2 by 1 matrix. So when we multiply for that first top spot, we're going to get 3/2 times 9, which is 27/2. and then negative 1/2 times 28 is negative 28 halves. We add those together to get the top entry of the matrix, which would be 27 plus negative 28 is negative 1/2. Now we do the same with the bottom row and the column. So negative 2 times 9 is negative 18. And 1 times 28 is 28. Adding these together, we get 10. So what this means is that the answer in this matrix equation is the matrix negative 1/2, 10, which is a column matrix. Example 2, let's now solve a system using a matrix equation. So our system is 5x plus 6y equals negative 14, x plus y equals negative 2. And we're going to try to turn it into a matrix equation, a times x equals b, where a is called the coefficient matrix, x is the answer or the variable matrix, and b is the matrix that holds the answer numbers in these equations. So we'll call it the constant matrix. So A is going to be a 2 by 2 matrix, X is a 2 by 1 matrix, and B is also a 2 by 1 matrix. So A is just all of the coefficients here. So that would be 5, 6, 1, 1. X is the two variables, so X and Y. And B is the two constants at the end of the equations. So now using the same idea as the previous example, when this equation was already set up, we want to solve for x, which is going to be equal to A inverse times B. So we start by finding A inverse. So 1 over AD minus BC multiplied by dA negative B negative C, or opposite B opposite C. So 1 over AD minus BC in this case is going to be 5 times 1 minus 6 times 1, so 5 minus 6, which is negative 1. So A inverse is going to be 1 over negative 1 multiplied by, we switch the right diagonal, so from 5, 1 to 1, 5, and then we change the signs of the left diagonal, so negative 6, negative 1. Now since this is 1 over negative 1 in front, really that's just a negative 1, so to multiply this out, we're just changing the signs of everything in the matrix. So A inverse is 1, negative 1, 6, 1, negative 5. So now to actually solve for x, we're going to compute A inverse times B. Which will be negative 1, 6, 1, negative 5, multiplied by negative 14, negative 2. We start by multiplying the first row by the column, which will be negative 1 times negative 14, which is positive 14, plus 6 times negative 2, which is negative 12. That goes in the top spot, and then the bottom spot will be the second row in the column. So 1 times negative 14 is negative 14, plus negative 5 times negative 2 is 10. So that gives the 2 by 1 matrix 2, negative 4. Now since x was equal to xy, it held both the variables in it. That means that this answer matrix X is equal to xy, which means that the top entry is x and the bottom entry is y. So the solution to this system of equations is x equals 2, y equals negative 4, or the coordinate point 2, negative 4, which would be the same solution that we would find if we solved this system by elimination or substitution or some different method.